Okay, so this is the triple point graph. This is the next graph on the list that you have. I know it's not really in focus, but it doesn't really need to be because you have the graph in front of you. Okay? So it's called a triple point diagram. We're going to be looking at a couple points. First of all, notice that this graph that you're looking at is, I know it's blurry, but I'm trying to video, so, and you have the graph in front of you, so it's okay. Let's see if we can make it a little bit better. No. All right. All right, so notice that this graph has no numbers on it because this is like a standard general graph. All right, and so it's not for any specific substance. And again, just like yesterday, every substance has this graph. And so there are two points we're looking at on this graph. The first is this triple point. And this triple point is, as you may remember from your vocab, the point at which all three phases of the substance can exist at the same time. So I want to be clear, this is not like, hey, I'm holding a glass of water that has liquid and solid ice in it at the same time, and oh look, there's a little steam going on above it for some weird, no, that's not what this is. This is the point on the in pressure and temperature where these three phases of matter exist permanently. So an hour from now, you will still have ice, liquid, like solid, liquid, and gas of that substance still sitting there. The ice isn't melting. The liquid isn't turning to steam. All right. Those three phases are still existing. And the reason is because the pressure is the exact pressure and the temperature is the exact temperature that needs to be for those three phases to exist at the same time. Yeah. Well, there is an example, but I mean, it's not an example that you know, but when we get to the water, you'll see what the temperature and everything is. All right, and we'll talk a little bit about it. All right, so the second point is the critical point, and the critical point is the point in time. Okay, so the critical point is the point at which the temperature is so high that no matter how much pressure you put on this gas, it will never go to the liquid phase. So no matter how much pressure, because remember, when you put pressure on a gas, you push those particles back together and you can compress it into a liquid. But the critical point is where the temperature is so high that you can't compress it back into a liquid. So that's what this critical point is. Now let's take a look at one of these graphs for something that we actually recognize, which is water. So this is water vapor. Now, water vapor, in particular, we can look at right here, which is 100 degrees Celsius. And at 100 degrees Celsius, we can go up to 1 atm, which is where we live at 1 atm. And we can see that at 1 atm, 100 degrees Celsius, we're right here. Excuse me. And that is the border between liquid and gas, water vapor and water. So that is, right here, is vaporization or boiling. That's what that is, between liquid and water vapor. So that is boiling right here. And that makes sense. 100 degrees Celsius, 1 atm is at that border, that line between liquid and gas. Does everybody see that? So now, if I go down to 0 degrees Celsius, 1 atm, I'm right here between solid and liquid. And so that is freezing or melting. So that makes sense at 0 degrees Celsius, 1 atm. Now, if we look at that triple point that we were talking about, that triple point is at 0.006 atm, which is very, very low pressure, and it's at 0.01 degrees Celsius. And that is a very unusual temperature, just above freezing. and a very low pressure, just above 0 ATMs. And at that point, this unusual point at just above 0, 0, that is where solid, liquid, and gas, water, will all exist at the same time. So is that something that we would normally see? No, it isn't something that we would normally see. But in a controlled environment, it is something that would happen. Now, where would ice sublime? Where would water sublime? So water would sublime down here between very low pressure and very low temperature. Well, where would you find that? You would find that in your freezer. And actually, it does sublime in your freezer. And that's why, if you've ever noticed, ice cubes, often old ice cubes, have rounded edges. If you've ever noticed that, if you look in your freezer, old ice cubes have rounded edges. That's because they are subliming. Your freezer is at low pressure. How do you know that? Because when you shut your freezer door, it goes psst. If you listen to it, your freezer does that. New freezers do that. Old freezers didn't do that, like the old white ones when I was growing up. They didn't do that, but they do that now. They do that now. When you shut them, you can hear them. They go psh, because they're lowering the pressure. And as they're lowering the pressure, what they're doing is they're setting up those ice cubes to sublime. And if you look at the ice cubes in your freezer, they have rounded edges because of that. So the next thing that we would want to look at is, why is it that we never see carbon dioxide as a liquid? And if you look, the reason we never see carbon dioxide as a liquid is because carbon dioxide is only a liquid at very, very high pressures. As in, like 1 ATM is right here, and that's where we live, at 1 ATM. And at 20 degrees Celsius, which is room temperature, right here, you can see that it's only a liquid there at about 60 ATM. Yeah. Atmospheres. So we are at 1 atmospheric pressure. That's what we live at, at sea level, 1 atmospheric pressure. So 1 ATM, but 60 ATM is about where carbon dioxide would be liquid at our room temperature. So you would have to go all the way down to about 56 or 60 negative 60 degrees Celsius in order to get carbon dioxide to be liquid at a reasonable ATMs, which would be 10 ATM. And at 10 ATM, it would be in your freezer at the grocery store. And then it would be solid, and you would pick it up in a chunk right here, about here. And then you would take it home. And when you get it home, right here, it would be turning to gas. So it would be subliming. So having liquid carbon dioxide just wouldn't even work. Even if you lived in Wyoming in the winter, you would not be experiencing it as a liquid because you wouldn't be at 10 ATM. So your pressure would be lower. So you would be much higher up than 1 ATM, right? Because you would be in the mountains. So you wouldn't be at 1 ATM. You would probably be at 0.88 ATM, which would put you here, even though you're at negative 20 degrees Celsius. You see what I'm saying? So you wouldn't be at 1 ATM, you still would be subliming. So having liquid carbon dioxide is pretty much impossible under normal circumstances. It would have to be in a lab. We just wouldn't experience it. We would experiencing it solid in a freezer in the grocery store, and then the minute we took it out, it would start subliming, which would be here. All right? So these graphs offer us, here is the critical point for carbon dioxide, which is 31.1 degrees Celsius, which is about 105 degrees Fahrenheit. So not even that hot. And that is the temperature at which carbon dioxide can no longer be experienced as a liquid at any pressure, because the temperature is too high. So those are the 2 points that you need to understand and be able to read the graph for the test. Yeah.